Hi there. So I'm actually giving this talk today on behalf of my line manager, Andy Kingdon, and our database manager, Martin Ninebell. And I'm going to talk to you about how we as an organisation use physical property data, some of the problems we have with standardising that data, and a bespoke internal solution that we put together. I will say at the start that it's not my talk, so if anything goes wrong, I'm going to blame Andy. So, just to give you a bit of background about the British Geological Survey. We're a public organisation, and one of our roles is to advise UK government, operators and the general public about risks and resources associated with UK landmass and UK continental shelf. And as time goes on, we're being asked ever more complicated questions about the subsurface. And to answer these questions, we actually maybe need to change the way we've been providing information in the past. So this is a nice example of the 1815 geological map from William Smith. And this is a great way to answer a question of where is something. But actually, as we go on, we're moving from where is it to what if, how much. A good example of this was back in 2011, where there was some controversy surrounding some testing at a Priest Hall well in Lancashire for shale gas. And at the time, the government came to us because they needed to know the location of resources and reserves, how much, and some of the technical constraints in their production. And this is typical of the kind of questions we're now being asked to answer. So answering that question was actually extremely difficult. It required a huge amount of data being brought together, so things like hand specimens, outcrop data, well data, seismic data. In fact, as you see there, over 15,000 miles worth of seismic data we had to put together. Now, the thing you'll hear most about this report is the final conclusion that the average estimate was about 264 trillion cubic feet in place, and it doesn't necessarily reflect the amount of work we had to do to actually get to that number. But it is a really good example of where we can use these geological big data sets because they really come into their own when we need to rapidly assimilate a large amount of data. Ideally, we want to automate some of that interpretation. And also, as been previously discussed, we need to better understand some of the uncertainties in this data and whether or not what we're seeing is actually reflective. So this bears a striking resemblance to the last talk, so apologies for that. But basically, it's just to talk about how some of the geological data fits into this definition of big data. So we talked about volume, so that would be the size of the data files, and actually variety as well. And I just want to make a quick point here that, sometimes the largest data sets that I've dealt with have actually been from CT scans. So you might have a centimetre cube of rock that's got a larger file size than potentially a 3D seismic survey over a large region. So it's sometimes it's quite difficult to try and bring all of that information together. Velocity, obviously, how quickly we can bring that information together, and I've mentioned about the uncertainty. We'll make a quick point about value, because ultimately that's what we want to do at the end of the day, extract value from this data set. And there's a lot of very, very high quality data sets in BGS that we like to work with, but inevitably they always tend to be in the places we're not actually asked about. So, increasingly, we're being asked to look at interactions between anthropogenic processes and the geology. So it's causing us to look at large areas, different types of data, different ages of data. As Mike, my colleague, mentioned previously, that we've been around since about 1835, so our data covers a huge range of time. And actually, to properly analyse this data, we need to make sure we standardise it first. We've been at it for about 20 years, so it's not something that we've arrived at quickly. So in terms of subsurface property data, there's a number of different types that we might want to try and integrate to answer a particular question. So that could be geomechanical properties, things like rock strength. It could be geotechnical properties, things like compressibility. Geophysical properties, things like density. Groundwater, things like water table depth, saturation. Geochemical properties, and a whole lot more. And we really need to be trying to bring all of these together to actually model these dynamic processes to make sure we can actually give an answer that is going to help someone. So in terms of heterogeneity, a lot of properties like physical properties like strength, porosity, permeability can have big effects on subsurface processes and can affect what you can do with a site. Now, typically, the only information that we've had to describe this is geological information. Now, this can often not necessarily be reflective of its physical properties. And again, like all our other data sets, there are problems with standardization. So when does a silty sand become a sandy silt? And whether or not two people would describe those necessarily in the same way. And the other issue is that increasingly we're being asked for information in numbers. So this is an example of a porosity model that we built for the Sherwood Sandstone. So that's a major aquifer unit in eastern England, particularly where I live in Nottingham. And we were asked basically, was there potential to store water in this unit? So we had to repurpose a huge amount of data, often from different sources and not necessarily collected to look at the Sherwood Sandstone itself. And by bringing together some seismic data, some geological modelling, we were able to create this. But we had lots of problems because we had mismatches between our data sets because they've been collected for different things at different times. It was also took us quite a long time to identify the appropriate data because of some of the corporate structures we were working with. So yeah, that probably brings us nicely onto some of the constraints that we sometimes work with. So non-digital data is a big one. The number of times that someone asked me about something that I don't have any digital information for, but I could probably get a paper record out and show them. Inadequate metadata, lack of standards, lack of upscaling medium. In terms of the metadata, I've certainly come across records where sometimes you're glad if they told you they collected the data about 10 feet from a church, because it gives you a fighting chance of actually finding it, whereas sometimes there's no information at all. In terms of the upscaling medium, a lot of people particularly been talking about working offshore, and usually when you're trying to upscale physical properties, you want to use like a seismic grid. But that's quite tricky onshore in the UK, because there's roughly about 31% of the landmass has got 2D seismic data available for it. So that's still 70% almost of the landmass that we have no large upscaling medium for. And actually, really, what you want is a 3D seismic survey, and that's 0.7% of the UK landmass. So we have a lot of problems in trying to work with this. Well, this is one of Andy's points, but it's probably worth stating. Only comparable data can be compared. And actually, when we start doing big data analytics or thinking about that, we need to make sure we've standardized our data set first. So we don't actually collect the majority of the data we use. A lot of the data is sent to us siloed from other industries. So we've got a couple of examples here. So we've got coal, civil engineering, water, and hydrocarbon. They're all collected for different purposes by different people at different times for different things. And to bring all of this information together, what our database managers created was a digital supermarket, or prop base. The idea of prop base was to make sure we had rapid, standardized data delivery. So to make sure that whatever data set went in, you always got the data out in the same format. So we have a lot of corporate databases within the British Geological Survey that deal with a lot of different types of our data. And I think in the past it was assumed that there was a corporate data store that sat between those and what we served to the public. But in actual fact, what we had was a series of incredibly complicated one-to-one relationships that sometimes actually weren't necessarily related to automatic processes. Someone might have just done a database dump and created a shapefile. So I'm sure if our database managers were here, they could tell you that in excruciating detail, but certainly it was the case that we had a lot of problems. So the idea with PropBase was to bring all of that information together and use an automated process to standardize that data and serve it in a single query layer. So all of that information, rather than having to go to lots of different places, was all suddenly within the same area, and then allow access to that to our scientists. In terms of the actual structure, so with a lot of the corporate databases we have, they have a normalized structure. So basically this means that there are pieces of information and there are data dictionaries and there are one-to-one relationships which govern what information is stored. So this is how things would typically look in our geochemistry database and then in our geotechnical database. Now this is really good if you want secure data storage, but actually if you want to look at querying this information and bringing it together, then it's actually quite inefficient. This is the prop-based data structure. So what it does essentially is it denormalizes the data and brings all of that together. So the denormalization is an automatic process, and then that allows for rapid querying of multiple data types. And then the key thing is that it's a standardized output. So if you've got something that will display one set of data out of prop-base, then that will display all the other types of data out of prop-base. It doesn't matter what it is or what it was collected for. Also, we make sure that we've got a link to the source database in terms of its identification, location, and audit trail. Because a lot of our data can only be used for specific purposes, so we have to be very careful about intellectual property rights. And just to reinforce that point, you always get a standardized output. So this is probably the slide I understand least about, but this is basically to show you that you've got a single data architecture. So you can put any data type in through the bottom and aggregate it. And then there is a two-stage process of first, denormalizing that data, and second, optimizing that data. And by doing that, you can rapidly then generate standardized outputs from multiple different types. So how do we use it to solve problems? Good question. So by giving access to all these multiple different data types, what we allow is to very, very quickly answer the question, what have I got in at X? Because actually that is a question that sometimes we found quite difficult to answer. So we can actually toggle on multiple different data sets and use spatial searches. So I can go to a site and I can say, you know, I want to look at this site, what has been collected there? Do we have geochemical data? Can that tell me anything about it? And the other thing, it's incredibly quick. So even though you're querying millions of records, you can bring out tables in standardized formats in like minutes, well, probably seconds for the most part. It's been a while since I've output anything from it. So in terms of what we're looking to do with this in moving forward, the UK government have allocated £31 million worth of funding to establish 2 geoenergy observatories onshore in the UK. So one will be at Cheshire, one will be in Cheshire, and one will be in Glasgow. Now, the aim of these observatories is to basically allow subsurface laboratories to test different new technologies and to output data. And what this requires is data structures and standards that are future-proof. So all of the information that we collect, we can serve in standardized formats to our end users to make sure that they can maximize the value of the data that is collected there. So the things that the observatories are looking at are issues related to shale gas, gas storage, geothermal, and carbon capture and storage. Now, some of these will require similar data sets, some of these will require different data sets. It doesn't actually matter because the data that we're collecting is all going to be run through prop-base, because you can have all kinds of information can be brought into it. So we've got a couple of things up at the top here, monitoring data, so that could be array or time series from baseline studying. It doesn't necessarily matter if it's not point data, you can bring that in. Geophysical logs, that's what I work with most of the time, so that's probably why that's there. But yeah, basically you can make sure that when you, once you've gone through this series of prop-base, you can collate that information, and then when you're serving that information, it allows you to timestamp it, it allows you version control. So it means that when you're running a large-scale project where, as you collect more information, your interpretations will change. You can actually defend those changes because you can say, you know, we did this interpretation with this version of data and we didn't know this at the time. We've now got that data and we've changed our interpretation, which is what we should be doing. So to sum up, really, in terms of looking at big data analytics, the first thing you have to do is to standardize your data. So this is a solution that we've put together just to allow us rapid access. And yeah, well, I'll probably finish up there.